Okay, so let's start. So where did we get last time? Last time I just told you that a way how to get non-commutative algebras is to take two possibly commutative algebras. You take A1, A2, and we take their tensor product. And if it is in a braided monoidal category, then this guy might be non-commutative. Now there was some more advanced formalism for that, which was that when you have two monoidal categories, or possibly braided monoidal categories, C2, then we were talking about functors that were monoidal or comonoidal or whatnot, and might have been braided monoidal or not braided monoidal. And monoidal functors will send algebras to algebras, but they will not send commutative algebras to commutative algebras, which is another way how to say how we're going to obtain non-commutativity. But frankly speaking, all interesting non-braided monoidal functors that will ever appear in this course will come from tensor products. So somehow this is the real construction. This is what, when it's maybe wrapped in some fancier language. Now, which braided monoidal categories we're going to use? Well, the ones that we've been constructing all the way, but let's call it. So at least some people call it Dreamfelds or Dreamfeld braided monoidal categories. So I'm just going to recall what we were doing all the time. So we had something that we called infinitesimally braided monoidal category. And infinitesimally braided monoidal category. What was it? That was a symmetric monoidal category C, which is also linear over some field, whatever of characteristic 0 that we choose. And which also has some first order deformation of the symmetry to a braiding. So plus some natural transformation, which is like T, there are AB, going from A tensor B to A tensor B, satisfying, now written slightly in some shortcut notation in the sense that I will not be writing those symmetries, etc. So such that TAB is equal to TBA. So the more official way is to, well, we need to flip first this AB here and AB there. So I should write symmetry and symmetry there. So I'm conjugated with symmetry, but this is what it is. And there was this infinitesimal hexagon, which was just triangle, which is just TA and comma, when there is a tensor product of two things, is just TAB plus TAC. So with this information, then when we created some kind of new braiding, beta AB, which was symmetry, AB and composed with 1 plus epsilon TAB. So this guy was a braiding where we had to pose that epsilon squared is equal to 0. And then we designed some machine to extend this first order deformation to a true formal deformation. So, but let me now summarize it because maybe we didn't see everything necessary. So maybe some notation. Let's say when, if say C is like there, it's enough to suppose that is a linear category, then by the C H bar, I will need to introduce some formal variable because our deformations will not be true. We will not have like the deformation parameter that would be a number. We will need to have a formal variable. So it's the same thing. So is the following thing. So the object CH bar the same as objects of C, and it's just morphisms that might depend formally on H bar. And home, AB in CH bar is by definition home in C between A and B, but now it might be family depending formally on this H bar. And you can imagine what's the composition, just multiply things. Composition is bilinear, so we can do it. And now say a little proposition, or one can also say Grand theorem, because this is why we were doing it all along, but it's also an obvious thing with everything that we know, is that if C is a infinitesimally braided monoidal category, then the CH bar with, say, the original tensor product, the original tensor product, and with yeah, I forgot something. I need an associator. So let me put it here. And phi, an associator of weight mu. Yeah, so we need this associator to extend that first order deformation to a formal deformation. So then the CH bar with the original tensor product, but with modified tensor product and with modified associativity constraint is going to be a braided monoidal category. So with beta AB defined as sigma AB, and now what you would expect, we apply this braiding, which would be the exponential of we were putting here something like mu divided by 2. Now the right thing to do would be just to write here TAB, but in general, I cannot do that because this wouldn't converge, or it doesn't make sense. So to say this is defined by a power series, so that's why I need to put here this H bar, and that's the reason why there is this H bar all along here. And with a similar thing, but where this convergence issue is even worse, one can say, and with rebracketing, so gamma ABC. So this is the thing which goes from ABC to ABC. So this is defined as, say, gamma ABC to old, the one, this invisible one that we had in C, the symmetric monoidal category, but pre-composed with, and now here put this phi, and since you see, what I did here, I multiply those TABs with H bar. That's the trick. If you multiply TAB with H bar, well, things are still satisfied, but I can plug it in, so that's the reason for multiplying. So I put here H bar, TAB, H bar, TBC. So this thing is a braided monoidal category. And why is it so? Because we were constructing associators exactly to satisfy that. So, well, so finally I just wrote it down, what we were doing. Okay, cool. And now, an example. Say some notation. I'll be using this notation that C H bar phi for this braided monoidal category. I should possibly also write mu somewhere, but let's say that it's implicit. Okay, now some example, the most important one for us. So we start with some Lie algebra. Now, because of applications, I need to call this Lie algebra D. And we are back to this problem of pretending that this is a fracture D. So we have a Lie algebra like this. Then we have some element, this is called T, which is something from S2 of G invariant. Now, mostly, or sort of everywhere in this course, this D is going to be, first of all, finite dimensional, and second of all, we're going to have a invariant product, or I should say probably non-degenerate symmetric bilinear pairing, because something like that. Invariant pairing on D, and that T thing. So this is something one can imagine is in S2 G star, G invariant, and this T thing is going to be.
So sorry, you have G and D?
Yeah. Yeah, so on top of that, there is this convention that G and D is the same until I go to the other blackboard where it all of a sudden becomes something different. Yeah. So this is somehow the basic or simplest example, the one which is used for quantization of Poisson Lie groups or Lie algebras. And then what was it? So then this C, which is the category of representations of D, UD mode. So this thing is naturally an infinitesimal braided monadic category. Is a BMC. What is this TAB? When we have two, well, it's a Siri notation for representations to call them lowercase a and b, but that's what I'm doing. I'm just doing silly things all the time anyway, so it's okay. So it goes from A tensor B, A tensor B. So how is it defined? You just imagine that this T, which is in S2G, so it's part of G tensor G. And so the first part is acting here, and the second part is acting here. So this guy acts here, that guy acts there, and that's our map. So that's the definition of this TAB. And yeah, that's all. And so in this case, then this whatever U D mod H bar phi thing is going to be sort of our friend or enemy or no. And this is what is mostly called the Drinfeld category. It's called So when we're going to take tensor product of two, say, commutative algebras to create a non-commutative algebra, it's going to happen here in this category. But to be able to do such a thing, we first need to even find any examples of any commutative or not algebras in a category like this, or in general in a category coming from this construction. So to do it, what shall we do? You see, this is a construction of braided monoidal categories. The construction is reasonably universal. I don't know, it's just the C doesn't enter too much into the description. So it should be also functorial in some sense, and indeed it is functorial. And so we're going to create some functors between some monoidal or braided monoidal functors between these kind of categories. So let me pretend there is a definition. So say, if C1 and C2 are infinitesimally braided monoidal categories. Then an infinitesimally braided monoidal functor f from C1 to C2. So what would it be? Well, first of all, it's a linear functor. Easy. Linear functor, which is also monoidal. Now these categories are symmetric together with this first order deformation to a braiding. So we want this functor to be braided with respect to that infinitesimally deformed braiding, but what it amounts to is simply saying that this functor is symmetric monoidal, that it just preserves the symmetry, so which is symmetric. So that's one thing. And it should also, there is one more thing to preserve. We preserve the symmetry, or this undeformed braiding, but we also want to preserve this little deformation. So it should also commute with T. Symmetric and commutes with T's. So what does it mean precisely? Well, monoidal means that we go from F A times FB, FAB, something like that. And what can we now do? You see, on this side, well, here in category C1, we have our T's, so we can apply T here and just use functoriality. So maybe let me write it here when there is enough space. It's like this. Phi A, phi B. That's our functor B monoidal, which has this thing. Now, here we can apply, okay, the full notation would be something like T, which is in this C2, and apply it on FA and FB. FA, FB. And the thing that we have here would be like F of T C1 AB. That's, I guess, the full diagram for saying what it means that it commutes with those T's. And okay, why do we need this? Because so these are functors which are somehow braided monoidal for that first order deformation. But at the same time, these same functors with the same monoidal structure will be braided monoidal even for that full deformation. So a little proposition. So if F from C1 to C2 is a infinitesimally braided monoidal functor, then the same F with the same monoidal structure, so with the same maps, well, I mean with the same morphisms, is a braided monoidal functor from this fully deformed C1 H bar phi to C2 H bar phi, and frankly there is nothing to prove, right? Because the braiding here is given by a formula. The braiding here is given by the same formula. It's only that once we're plugging in t's who are in C1, once in t's who are in C2, but that functor is supposed to preserve those t's. That's it. Also, like this associativity constraint, this gamma, it's given here by some formula, but it's by the same formula here. That's the reason. So it's very easy to prove things like that. Especially if I don't write anything, then it's very easy. Okay. And so in particular, how about algebras? Can we find some algebras, maybe just say a recall. Though it's going to be a little bit modified recall. So I will denote by 1. I need some sort of trivial infinitesimal braided monoidal category. So is the infinitesimal braided monoidal category with a single object. That I also call 1. I guess it's against the axiom of regularity or whatever, how it was called. But then the thing that I need to change, it's sort of a very stupid change. I need to have this category linear. So we used this kind of category before when there was a single morphism from going from 1 to 1. Now I need to sort of multiply that morphism by arbitrary numbers. So that's it. So hom 1, 1 is equal to k, and t is equal to 0. 1, 1. So let's sorry, this, yeah, inference braid it like this. Now I will denote the same notation for the corresponding braiding thingy. Okay, so let's have this. And now suppose, say, if we have a functor going from this 1 to C is a braided, infinitesimal braided monoidal functor. And what happens if I apply there this phi thing? So then the same f, but going from 1, I should put this h bar and phi going to C is just a braided monoidal functor. There is nothing infinitesimal anymore. But who is this guy? You see there, this is our first example where we're applying this Drinfeld's construction on something where there is no deformation whatsoever. When t is equal to 0, then t is equal to 0, so nothing is deformed. In all those formulas, things are just equal to 1. So this thing is simply equal to 1. Maybe I can put here this h bar if you really want to have it there. But it's still just the same trivial category as before, with a single object and nothing happening there at all. And now if you recall, what is a braided monoidal functor from this trivial category to a braided monoidal category? That's the same as a commutative algebra. And it is f of this, this wonderful notation of 1 as an object of 1 is going to backfire. So f of 1, that's this object, which is a commutative and associative algebra in that C, and f is fully given by this stuff.
So in the second line, is there C or C5?
Yeah, that's this thing. Yeah, so because we somehow want to construct algebras in those rather non-trivial braided monodal categories. They are non-trivial in the sense that there is this horrible phi for which we do have an example, but even that is kind of with all those multi-zeta values. Okay, so f is, well, determined by this algebra.
Sorry.
Yep.
When you say that one H bar is exactly the same as one, the morphism should be.
Yeah. So. Yeah, that's right. So morphisms here are now formal power series. Okay. Yeah. 1 is k. So somehow these functors are always linear over Kh. This is linear over K. So we just introduced this formal parameter because we had a convergence problem. Now we have to carry it on, but everything is just going to be linear with respect to that, so everything is fine. Okay, so this is a way how to construct commutative algebras. And that's a good start, right? So to that, we should understand what are these things. So what it means to be this. What is the thing that it is a braided, infinitesimally braided monoidal functor from this unit category to some infinitesimally braided monoidal category C. So what is that? Well, first of all, it's a symmetric monoidal functor going from 1 to C. So the first thing, it's a commutative algebra, certainly. So let me call it, I don't know, A. F of 1 is a commutative algebra in the symmetric monoidal category C. That's one thing, but it's not just commutative. It's not commutative only with respect to that symmetry. It's also commutative with respect to this first-order deformed braiding. And what does it amount to? And such that I'll draw it with a picture, though it's possibly easier to understand if I write a formula. So here are somehow A. This is the multiplication. Let me call it this M. And it goes from A tensor A to A. So there is this additional thing that when we apply here is T. So this is what is TAA. That this guy is equal to 0. Okay, just this. That's something fairly simple. So now in whatever examples we might have, we would be just looking for commutative algebras which satisfy on top of that this equation. And let's try to understand what's happening for the Dreamfeld's example. So when this C are representations of some Lie algebra with a fixed element T, or maybe with an invariant inner product. And okay, I will maybe write it in some reasonable geometrical way because we in the end want to apply it for deformation quantization. So let's go away from algebra and let's do it purely geometrical. Though there would be some obvious, more algebraic versions of this proposition. Now I probably imagine that D is a real or complex Lie algebra. So okay, is R or C. But otherwise, you just have to rephrase it in algebraic geometry. Otherwise, this is the same. So suppose we have what we start with. Okay, whatever D is a Lie algebra over this K, is there. D is somebody who is from S to D, and now suppose M is a manifold with an action of D. So why do I need this? Because now I'm going to pick up this algebra, and for A I will take C infinite functions on M. So certainly that A is a commutative algebra in our. So A is a commutative algebra in the category of representations of D. In UD mod. Yeah, it is an algebra in that category. That's exactly because our D acts on A by derivations. So that's what it amounts to for being an algebra in categories of representations. And the thing is now, so then A is, I didn't have a notation, so let me call this the thing that A is, this is really silly notation, but let me call it I commutative. It just means that it's a commutative algebra which satisfies also that thing, and it's compatible with the notation that I was using up to now, but it looks somewhat weird. Okay, so then A is I commutative. If and only if, for every point, for every whatever x in M, the stabilizer of that point, the stabilizer, we call it like dx part of d of x, is a coisotropic, or maybe d coisotropic Lie subalgebra, or such subspace. D, what does this? There are many ways how to say that something is coisotropic. Here, the best way how to say it here, that if we start with D tensor D, that's where D lives. dest. And now project it to d mod dx, tensor d mod dx. So then this t, which lives in this section, goes to 0. Okay, let's try to prove this thing. So what do we need? So we just take, say we start with f and g, two functions, two things which are in C infinity of m, and then we need to apply that thing. So we apply t, t, whatever AA you wish, applied to f tensor g, and then so this thing is still happening in A tensor A, and then we need to apply m. So this should be something reasonably geometrical. Because you see, what is this thing? This TAA. This by definition, okay, I don't know how to write it, it's something like rho tensor rho. Where we plug in t, who is in t is in d tensor d. Right? Then we apply it there, and then we take the product. But what does it mean to apply rho tensor rho and then take the product? That's the same thing as should I write it? Okay, so we have this m, which we apply on rho tensor rho of t, and all of that we apply on f tensor g. And the outcome should be a function, right? So it's again, this guy is again C infinity of m. And the idea is now to say make the composition here. So what is really happening there? It's I can put it that way. I have trouble with notation, but let's see. So we have this. Okay, let me put it this way, that for any x, we have in M, we have the map rho x going from D to TXM. It's just our representation. And now this thing is simply, so then we can take, let me call it Tx. That would be rho x tensor rho x of t. So that's something that lives in T tensor T, or of S2, because it's symmetric, S2 of T of X of M. And then this horrible function this horrible function computed at point X is nobody but simply like this Tx, which acts on or is paired with, if you wish, or maybe let's move this way, the Tx where we plug in df and dg. It's just this thing rewritten when we want to compute it at some particle point. This is what we get. And so we want this thing to be 0 for all f and g. This dx of df dg to be 0 for every x and g. So this simply implies that dx is equal to 0 for every x. But now it should be sort of clear, because what is now happening? But how do we go with this t to tx? We can say that we go from d tensor d. First we divide by the kernel, so we go to d mod dx tensor d mod dx. And then once we're here, then our map going to tx tensor tx is injective because we killed the kernel. So we start with t, who is here, and it's mapped all the way here to 0. So it means that t is mapped already here in this projection to 0. Hence, therefore, t goes to 0 under the projection d tensor d mod dx tensor d mod dx. Okay, that's roughly what's happening. So it seems that this is a reasonably geometrical thing to describe those commutative algebras in the Drinfeld category. Yes, so just before the break, maybe to some little remark. Because this is what is mostly going to happen, is D is going to be a Drinfeld double of some Lie by algebra. So if, say, D is whatever finite dimensional, with some non-degenerate pairing, invariant pairing, on the, and the T is simply the inverse of our pairing, then what it means to be coisotropic, I know some G part of D is this T coisotropic. That's if and only if it is coisotropic in the normal sense, and if and only if when we take the things who are orthogonal to G in D when it's part of G. This is one thing. So in particular, we definitely saw some examples. Say if you have if D, G, and G star is a Riemannian triple, then those G and G star are coisotropic. They are even Lagrangian. They satisfy equality, but well, all the better. That's already some important example. And then how to find some example of these kind of things. Say, if say G is coisotropic, and let's suppose that we take the corresponding groups G, D. Let's suppose that this one is a closed subgroup to make it correct. So if this and if this is closed, so in this case, then M defined as D mod G satisfies the assumptions of the previous proposition that is just when you take C infinity of D mod G. So this guy is a infinitesimally commutative algebra in the category of representations in UD mod. Okay, so this is sort of, now everything is done in a way. That we have examples, geometric looking examples of algebras who are commutative. And then we'll be only taking their tensor products and obtain everything that we want. Okay, so let's have a break. Okay, so let's restart. So we just had this example that I erased, which is that C infinity of D mod G is that infinitesimally commutative algebra mu D mod. So this is some kind of more geometric version of some other statement that I can write now and leave it as an exercise. So this more algebraic statement, which doesn't talk about C infinity or anything, is that when you take, let's talk about coalgebras. So when we take UD and modulo from which side should I, like this, UD times G. That's a subspace here, or it's whatever. It's the ideal generated by G, I think, or no, sorry, not. It's a submodule, sorry, generated by G. It's also ideal, but doesn't matter. So this guy is a I co-commutative coalgebra in the same category in the UD mode. So for that, part of the exercise is to define what is I co-commutative coalgebra, but you can probably, I can solve this part of the exercise. It's just everything is upside down. And this thing is equal to 0 for this coalgebra, which is defined, well, that's a coalgebra. We mod out by something. It still is a coalgebra. That's it. Okay, that's nice. So now we can create some commutative algebras in this relatively difficult-looking braided monoidal category, right? So where are we now? We know that C infinity of d mod G as an object in this U d mod H bar phi. So this stuff is a commutative algebra. So we don't need to do anything with this algebra. It says the original product. We didn't deform anything. We deformed only the category itself. But even after we deformed it, this stuff stays a nice, wonderful commutative algebra. Then we can take two such things. We can take their tensor product, or if you want to stay geometric, then we would take probably a completed tensor product to have like C infinity of the product of the manifolds. We would have a non-commutative algebra in the same category, but then we don't care about non-commutative algebras in this strange category. We care about algebras in vector spaces, about ordinary algebra. So we need to go some kind of back from Drinfeld's category to vector spaces. And so that's going to be some sort of example / proposition. So let me write it here. The statement is simply that if, let's use the same kind of notation. So if D part of, the G part of D is a coisotropic Lie subalgebra, then the functor which is going from U D mod just to vector spaces. I will take the functor which sends, sending V to G invariance. So this guy is going to be naturally a monoidal functor. What is the monoidal structure? With the monoidal structure. So for that, what do we need? We need to go from BG tensor WG to V tensor WG. And there is one map which is totally obvious, right? These are invariants under a diagonal action. These are invariants under both left and up under both actions. So this is simply being the inclusion. So this guy is a infinitesimally braided monoidal functor. So what is there to be proven? So what is an infinitesimally braided monoidal functor? It's a symmetric monoidal functor. So this, what we call this, F. F needs to be symmetric. And sure, it is symmetric monoidal functor. There is nothing to verify here. Yes, that thing is okay, but it also needs to commute with those T's. So we need commutes. Can I close it? Or I don't know. I just cannot hear myself. Maybe it's okay. Maybe that's what everybody prefers, but. So let's verify that this F indeed commutes with these. So what does it actually mean? What we need to verify? So this, I didn't tell you in the proposition what is the infinitesimally braided monoidal structure on vect, but it's just 0. So here, T, A, B, or T is equal to 0 in vect. We don't want to deform anything in vect. There is no means how to deform anything there. So what we need to verify is that we have VG tensor VW. Now here is this monoidal structure, which is this inclusion going to V tensor W. G. Now here we would be applying T in vect. But that's simply 0, right? So we're putting here, this arrow here is 0. And the thing that we're putting here, what is it? It's the so to say, oh well, we just take this row tensor row or row V, those two representations. So it's like row V tensor row W, and apply on this T, who is in S2, who is in D tensor D, this way. And simply restrict it to G invariance. We want to see that this commutes, but what does it mean commute? Well, this is just inclusion, right? Inclusion. So we want to see that this map restricts to 0 when you use it on G invariance tensor G invariance. That's what we want to see. Want to see that row B tensor row W of T now restricted to VG tensor WG is equal to 0. But why is that true? But that's true. But we know that when we take this T, who is in D tensor D, and map it to D mod G tensor D mod G, then this guy goes to 0. And you see that T is going to act only through this projection here. So on those invariants, once we're on these invariants, then the thing, well, once we apply those actions, it's only the image in T mod G tensor T mod G that matters, because this G part doesn't act there. Those things are invariant. So therefore, the only thing that matters is the image of T under that projection, but it's 0. Well, that's all. So it's sort of the same argument as before. Cool. So now we found some infinitesimally braided monoidal functor. going to vector spaces. So as an outcome, so this implies, that's why we're doing it all the time, that when you start with this difficult category UD mod H bar phi, with this guy, and now we apply that functor going to vector spaces. I need to put here this H bar. No, H bar is not going to go away. Just take this, and let's take this functor of V going to G invariance. So this is a braided monoidal functor. So in particular, when you have an algebra here, it will go to an algebra there. If that algebra happens to be commutative, then it will go to a commutative algebra. We don't care too much about constructing commutative algebras in vector spaces. It's more like that we care about constructing some non-commutative algebra here, then applying this functor, and it will go to something, hopefully non-commutative algebra there that will be interesting. And as an example, so let's start with a D, G, G star, a Manin triple. Now I'm not supposing anymore that G is a closed subgroup in D. That's an artificial assumption, but we have, let me explain it this way, that there is we have some local diffeomorphism between G and D mod G star. So you see that G star is not necessarily a closed subgroup, so this thing is defined only, say, locally or as local groups or something like that. But how is it given by the inclusion G part of D? And I'm using this local diffeomorphism only to say, so this implies there is a natural action of D on G. I think we once even met this action somewhere in exercises, with this thing, at least part of the action, which is called the dressing action, but whatever. So there is a natural action of the Lie algebra, right? So we don't really have action of the Lie group if we cannot identify these two spaces. So this is really just lock everywhere nicely, but just the local identification is perfectly enough for having a Lie algebra action. And with the stabilizers, well, always just conjugate to G star, and therefore they are certainly quasi-tropic. Okay, cool. So on the group G, there is a natural action of the Lie algebra D. As I said, it doesn't necessarily integrate to action of the group itself. It depends on how things are arranged. But what is important is that the stabilizers are just conjugate to G star, therefore they are coisotropic. So that implies C infinity of G is a commutative algebra in Greenfeld's horror, mod H bar phi. So what can we do now? Say the same stuff would be true for C infinity of G star if you wanted, but we can stay just with this. So that now implies that when we take, say, two copies of this algebra, C infinity of G, tensor C infinity of G, it's a little bit maybe of cheating if I put here this hat, because that's not really a tensor product in our category. I should probably redefine a little bit the category to say that there are some topological things so that we can have this completed tensor product. But if not, just erase it and don't worry about anything. So anyway, this stuff is an algebra in the same category. And then, so with this completed thing, we can identify it with C infinity on G times G, but okay. Without that we cannot, but it doesn't really matter. And now to descend to vector spaces, so this implies then that the C infinity of G tensor C infinity of G and invariant functions here is an algebra just in this vector. We just constructed an associative algebra in vector. Now, what exactly is that thing? You know, there was this, well, not very mysterious action of D on G. So to understand that, so the action of G, which is part of the so what is this guy? You see, what was the action of D? The action of D is just the action on D here by left translations, but then we need to somehow project it down to G. But the action of G as a part of D is simply by left translations, but then there is no work projecting it back to G, right? It just stays within G. So that's why this action of G on G is simply by left translations. Or by whatever, right invariant vector fields or something, I don't know from which side. And now, so what are the functions which are invariant under the joint left action of G on G times G? So therefore, so this implies that C infinity of whatever, it's just G times G and G invariant thing. So those are functions that depend only on, so this one can be identified with C infinity of G via how would I put it? Probably here, if there is some F1 who sits in here, and then there is F2 who sits in here. So what is the formula? Is that F2 of G1, G2 is the same as F1 of G, like this, probably G2 inverse G1. Yeah, I guess this is what would kill this simultaneous. If we multiply on the left by somebody here and somebody from there, then it just, and the function is supposed to be invariant. That's the same as saying that the function really depends only on this product of those two things. Or maybe I can write it, maybe it's nicer to write it like G1 inverse G2. I'll keep the order here and. Okay, so what did it do with all this horror? Well, we'll look at it again with some nicer notation. But what did we find? In the end, we found a product on this space. So. Associative product, let's call it star, on C infinity of G. What can, just from general considerations, what can one say? When it's set H bar equal to 0, then there is no deformation happening anywhere in anywhere that I wrote. So this product modulo H bar is simply equal to the original product. So with some kind of deformation, you see that product is in a home, whatever this vect H bar of A tensor A. So it's something that depends formally on H bar. That's why it's some deformation of something. And so this thing, so this star is a star product. And in fact, as you might have imagined, that's why it's happening, it's a deformation quantization of the Poisson structure on the Poisson Lie group. And it's a quantization of the Poisson bracket on the Poisson Lie group G. Okay, so we just found a deformation quantization of those Poisson structures. Sure, one needs to verify that stuff. The best way how to verify, or the thing that we still need to really do, is to persuade this thing with this new product not to be just an associative algebra, but to be a Hopf algebra. We want to really deform C infinity of G as a Hopf algebra. And from there, once it's a deformation as a Hopf algebra, it's way more natural that it's actually a quantization of some Poisson Lie group structure, and it should be easy to see that it is the only thing that it might possibly happen. But one can also compute it directly, and one might be able to do it in some exercise. So for the moment, I'll just keep it like that. Say it's true, believe me, what else could it be? It might be also 0, as it happened in one exercise this week by my mistake. But yeah, it's just true. But to see better what's happening, we shall have a look at Hopf algebras. Now we don't have too much time, but let me start. So what is that thing? So in principle, that's something which might happen in any braided monoidal category. So say, first of all, if, say, C is a braided monoidal category, then this is a thing that we saw, that when you have two algebras, then their tensor product is again an algebra. Or when you have two coalgebras, then their tensor product is again a coalgebra. So what we can summarize it by saying that the coalgebras in a braided monoidal category form a monoidal category. The coalgebras in C form a monoidal category. This category is no longer braided monoidal category, it's only monoidal. And what was the monoidal structure? If you remember, the thing was you need to say what is the coproduct on tensor product of two coalgebras. The idea is to define it this way. Or for the algebras, it's the same picture but upside down. So that's the definition of the tensor product. And now a definition by algebra in C, that's the same as an algebra. I mind that whenever I say algebra, officially it means monoid, and whenever I say coalgebra, it officially means comonoid. So it is the same as an algebra in the category of coalgebras. In C, or if you wish, it's the same as a coalgebra in the category of algebras in C. But say, if you want to see it more concretely, what it means, it's a thing which is both an algebra and a coalgebra. And those two algebra and coalgebra structures, they should be somehow compatible. And what the real thing which somehow appears here is that when we apply that coproduct on tensor product of two copies, so that's how it's defined there, right? So we do this thing. And then we do those products. So then we do this, and this should be the same as just taking the product and then taking the coproduct. So that's somehow if you want deciphers what it means to be algebra in coalgebras, then one gets this sort of more symmetric looking picture. Okay, and finally, so this is a bialgebra, and finally there is the thing called Hopf algebra. The Hopf algebra is a bialgebra with an antipode. So that's a morphism. It's a bialgebra with A, S going from A to A. An antipode means that it's something that satisfies. And when you split it and apply this antipode here and take the product, and this should be the same thing as when you take the counit and then unit and that thing, and it should be the same as this. So I guess you met these kind of things in quantum topology course last term, right? So I don't need to give details. Probably the notation that people are using for this S is like that. So I might use it this one time and stop using it from now on. And I will actually suppose it's not maybe not a part of the official definition, but from now on S is supposed to be invertible. Somehow it seems that those Hopf algebras with invertible antipode are sort of nicer than others. And we'll be only getting these. Okay, and now we want to get those Hopf algebras. This is our goal, somehow to get better understanding of quantization of Lie algebras or Poisson Lie groups. And how are we going to get it? So I'm not sure, I probably shouldn't just write it because it doesn't make any sense. So the general idea is that the Hopf algebra is sort of a non-commutative version of a group. It's somehow both non-commutative and non-co-commutative, so it's like a group in non-commutative geometry, whatever it means, but it means precisely this definition. And a group, how would one get a group? Often as the group of symmetries of something. And so then one just needs to redesign what it means to be the Hopf algebra of symmetries of something, what that something means and what symmetries mean, and things like that to find the Hopf algebra. So that's one way how to get it. That's a very natural way, and we will not use this way. So the way we shall use is some other thing, just looking at the group as it is, using a bit of some formalism, which I will just probably write the name. Start. So we'll talk now about simplicial sets. Let's look at simplicial sets and simplicial objects. Now, so what is the idea behind whatever my decision to talk about this? Is that my feeling is that I was trying to avoid all kind of formalism in this class, and it always backfired. Like I was trying to avoid giving a definition of an operad, and then I was using operads all along. But that was a great touch. So what's going to happen now? I'm going to give you some formalism, and then I'm not going to use it. So at least to somehow to compensate a little bit for both of these things, let's do it this way. I don't really have to. The only thing is that I sort of imagine that many of you already know what is a simplicial set, or all of you maybe know what. No, not all of you. Okay, then maybe it might make sense to talk about it. So let me give you a definition which is going to be mysterious. As usual, so definition is, so first of all, one defines what is the simplex category. Or I hope it's the right name. Category, which is called delta. So object. So one way how to say this is a non-empty, finite, totally ordered. Or sets and morphisms are the order preserving maps. Now there are some standard objects there, which will with notation for n with some object. So there's just this set 0, 1, 2, with the usual order, like that. And if you wish, and people mostly do that, they just declare that this category contains only these objects, but it's perfectly okay because every object, every finite non-empty ordered set is just isomorphic to one of those. So it's fine to use either of these definitions, either to have just these objects or to have this huge amount of objects. Now, why does one imagine this category of simplices or something like that? Some kind of remark to understand this better is that, okay, I can say there is a functor, but doesn't. Okay, let me say there is a functor, or there is a realization of this category by something concrete. Delta, but probably the right way how to say it is really a functor going from delta to top to the category of topological spaces. The idea is to send to n, or imagine n as the geometric n simplex. So these are all, I'll just be using the same kind of notations. So these are all kind of T1 less than, or okay, no, I will not use any notations, just n simplex, say with vertices. Which will be called the same numbers as are those elements in this n, 0, 1, 2, up to n. And then whenever you have a morphism, you go from n to m. So then the corresponding, so this is sent to, yeah, then now this kind of thing is sent to a map going from delta m to delta n to delta m. And what is this map? Is just the affine map sending vertices to vertices. No, each vertex to its corresponding vertex. So all this delta thing is just some kind of abstract way how to think about simplices and faces of simplices and possibly some degenerate maps of simplices, things that somehow collapse simplex and things like that. Anything else? Probably not. Now, so what is a simplicial set? Simplicial set is the same as a contravariant functor. So something going from delta up to set. And what would be somehow the first type of topological example? So if you have whatever X is a topological space, then if you take all singular simplices in X, the singular simplices in X form a simplicial set. singular simplicities are all continuous maps from simplices to X, and they will form a simplicial set. So this is somehow the thing which happens for any topological space. Now, but in general, if you have a simplicial set, so how should one imagine it? One should imagine that for each n, that set corresponding to n is sort of set of n-dimensional simplices. And all these order-preserving maps, they just tell you who is the face of whom, how to pass from, say, from triangles to edges, who are those edges, and things like that. And so for today, that's all. We shall continue next time.